In the What is an electrical control panel video, I just pointed out the enclosure of the electrical control panels. But today, and in the next parts of this video series, we'll take a closer look at them, so that you can make an educated decision on choosing your electrical panel by end of this video. Although we will dive deeper and also talk about some other devices like cable glands or cord grips, and some useful tools for working with the enclosures. You'll also learn about the IP rating and NEMA rating of the electrical panels and other useful things. If you happen to visit a factory in any industry, I'm sure you've seen various types of electrical panels with different sizes on the factory floor or inside of its electrical and control rooms. There are wall mount and floor mount enclosures in terms of installation method. Sometimes when the designer is searching for the best place with the most accessibility for installing the remote I/O panels around the factory, he or she might find it difficult to use the panels with the floor mount or standalone cabinets. So they better use the compact and wall mount types. I'll explain about remote I/O and expansion I/O panels in a future video. Needless to say, there are additional reasons for reducing the size of panels. For instance, the larger the enclosure, the more metal is used on making that. The end result would be a higher cost. Inside of the control or electrical room, it is most likely that you only see floor-mounted cabinets. If you have ever noticed, in some electrical rooms, the cables are coming from the top side. In some others, the cables are laid on the bottom. You should examine the cable entry of the floor-mounted cabinets in the design phase of the project. Should they be top entry or bottom entry? It actually depends on the architecture of the room. If there are cable trenches, cable tunnels, or raised floors in our project, then we can pull the cables through the floor. In this picture, you see the power cables are entering into the switchgears from the bottom. Yet, if there would be a concrete surface beneath the panels, then there is no way except to choose the top entry enclosures. Pull the cables from the cable trays hanging from the ceiling of the room and bring them inside via the gland plate on the roof of the cabinet. What is a gland plate? A gland plate is a detachable metal sheet on top or on the bottom of the panel that is a part of the enclosure. We should drill the gland plate to bring the cables inside the panel. To drill a clean and polished hole on the gland plate, we need appropriate tools like hole saw cutters for steel or stainless steel plates. We also need a metal reamer to polish the edges and to further adjust the size of the hole. So first I drill the hole using the hole saw cutter. Then, as I mentioned, I use the reamer to have a clean and polished hole. After I drilled all of the cable holes that I need on the gland plate, I should reinstall and fasten its screws. But before passing the cables through the holes, there is another component that we should add, known as a cable gland. A cable gland, which is also called cord grip or cable fitting, is a piece of plastic, stainless steel, or even aluminum part with the standard sizes to provide proper cable connection to a device. For instance, if I need to attach this cable to an electric motor terminal box, I first need to dismantle the gland and install that on the cable. Then I will bring the cable inside the box. Finally, I fasten the cable gland to the terminal box using its hexagonal lock nut. In this way, the cable is protected against any kind of possible strain. Moreover, it seals the motor terminal box and prevents entry of water or any kind of liquid into that. There would be the same procedure as the motor terminal box for the electrical panels. This time, after I install the gland on the cable, I will pass it through its specific hole on the gland plate. I adjust the length of the cable that I need within the electrical panel and then fix the gland on the gland plate. Here you can see some cases of installed glands on the gland plates on top or on the bottom of the panels. As you see, the cable glands are applicable for all kinds of the cables like power or instrumentation. To state the obvious, the size of the holes we should drill on the gland plate depends only on the size of the cables we're going to bring into the panel. Accordingly, the cable size will determine the appropriate cable gland size. As you see, there are standard charts for this purpose. As a side note, in some electrical panels, motor boxes, or VFD panels, we might see some pre-installed pyramid plastic parts known as cable entry grommets. These are for routing the large or unknown size cables and are more flexible compared to conventional cable glands. As you see, the diameters are marked on them so that you can cut them from the appropriate place. An important point about the electrical panel enclosures is their ingress protection rating, or IP rating, and their NEMA rating. The IP rating, which you can usually find on a label within the enclosure, is a two-figure code that shows the level of resistance against dust and liquids. For example, a device with an IP55 level has limited ingress protection against dust, and of course, low-pressure jets of water from all directions. NEMA ratings have the same meaning as the IP ratings, but with different styles, and most of the time you can match a specific IP rating with a NEMA rating. We'll create a comprehensive video on IP and NEMA ratings. So if our electrical panel has an IP55 rating, after we have entered the cables into the panel, it must still have this degree of protection. Thus, the glands will help us to maintain the IP rating of the electrical panels after the cabling works. Meanwhile, the ingress protection rating will be increased by some specific tapes around the doors and the gaps between the side plates of the enclosures. There are different types of glands from type A to type E, and each are made for a particular purpose, which we will talk about them later. Some specific types of glands are made for hazardous climate conditions and areas to prevent the entry of flammable gas or vapors into the enclosure of the equipment. These types have ATEX approval and are known as flame-proof or explosion-proof glands. There were lots of different information to take in. I think it's enough for this part. In the next video of this series, we'll check out some other properties of enclosure and electrical panel fabrication. Thanks for watching, and don't forget to click the like button. In this video, I'm going to talk about some aspects of the electrical panel enclosures you most probably did not consider before. I will discuss the bearing system configurations, the enclosure compartments, wiring ducts, and so on. This is the following part of the electrical control panel series and their enclosures. So if you've missed the previous parts, watch them before this one. As you have seen in the previous part, the panel has a steel sheet inside, known as the mounting plate, that we have to dismantle and install some wiring ducts on that before we do anything else. Ducts are a kind of organizing component that we route the wires inside the panel using them. I'm going to add another point here about wiring ducts. As you see in this electrical control panel, in some routes we have more wires, and in some others we have fewer. So we should consider the depth and the width of every piece of wiring ducts according to the volume of the wires we're gonna lay into them. It is not only about the size of the wiring ducts, but the dimensions of the enclosure have also a significant impact on the comfort of wiring and installation of the electrical components inside the panel. Obviously, the more electrical components we have to install inside the panel, the bigger the size of the electrical panel should be. In addition to the number of the components, the purpose of usage can also impact the size, type, and configuration of the enclosure. Generally, an electrical panel enclosure is comprised of a chassis or frame and some plates on its different sides that can be dismantled and assembled pretty easily to provide different configurations known as enclosure baying systems. Let me give you an example. Consider this motor control center or MCC panel. This panel has 3 separate compartments with different dimensions that are attached to each other. The left one contains the mains power bus bars. The middle enclosure consists of several other compartments, each one assigned to a circuit breaker of a specific electric motor. These circuit breakers take the power from the bus bars, and in the right-hand side compartment, the cables will be connected to the output of the circuit breakers and transfer the power to the electric motor terminal box. This electrical MCC panel is actually a kind of side baying system in that separate panels are connected side by side. As you see here, depending on our requirements, there could be other baying system configurations as well. In these systems, as all of the enclosures are connected to each other, they have potential equalization and therefore provide more safety, and we do not have to earth each of them individually. Generally, there are standard dimensions for the industrial panel enclosures that we can choose among them when we are designing our electrical panel. However, you might see some custom size enclosures in particular applications, such as these freestanding VFD or variable frequency drive panels. We can also choose 1-door or 2-door panels depending on the width of the panel and our desire. As all of the electrical panels have a metal enclosure accommodating many electrical and non-electrical devices, they are pretty heavy most of the time. Therefore, to lift, move, or install them using a crane, the enclosure manufacturers consider lifting eyebolts directly on top of the frame corners. After the placement of the panel in its final position, we should fix them in there by bolting their bottom frames to the ground. We talked almost about every aspect of the electrical and control panel enclosures except the color. Same as the other properties of the panel, the color also has a standard. Basically, the color of the enclosures is determined by the RAL standard color code, which is a 4-digit number. For instance, this electrical panel has the RAL 7035 light gray color. That's it for this video. Thanks for watching, and don't forget to click the like button and share this video with your friends and colleagues. Behind the scenes of every factory, there are lots of electrical panels that make the process work properly. These electrical panels can be distributed throughout the process or located in a special room like control room or electrical room. The electrical structure and architecture of a plant could be the story for another day. But in this video, as you've requested in the comments, I'm going to talk about one of the most important electrical panels, which is the electrical control panel. So stay tuned to the end of this video to get some practical insight into electrical control panels. The number and the size of the panels may strongly vary depending on the type and scale of the control system. For example, the control system is DCS, then we might need up to 4, 5, or more separate control panels. The control system is PLC-based, then one single door or a double door panel could be enough. The first is the enclosure, which houses our internal devices. I'll explain more about the enclosures in a future video. The internal devices should be installed on a thin metal sheet called the mounting frame or back panel. The first piece of component to install on the mounting frame is the DIN rail. DIN rails are some long metal strips with a standard size and some holes in between that we need for mounting the electrical devices on that. In other words, instead of installing each piece of component separately, we can snap and click the components into place easily. So, we cut and install them according to the panel design. The second piece that I'm going to install on the back panel is the wiring duct. You'll see that how wiring ducts will organize and cover the wires within the panel. After we cut and install the ducts inside the panel, let's get into the electrical components of the control panel. First things first, we need electrical power inside the panel. Depending on the electrical system architecture of the plant, in some of the control panels, we have a three-phase power entering into the panel. Yet, in most of the middle to huge size projects, we supply the control panel with only a single-phase power. Now, assume our single-phase power is entering to a two-pole miniature circuit breaker, or MCB. This electric power comes from another panel within the electrical room, like a kind of low-voltage power distribution panel. Either way, the MCBs are a type of protection circuit breaker that are used in the entrance of the panels with different consumptions up to 25 amps. They protect our panel from overload and short-circuit faults. Furthermore, we can connect and disconnect the whole power to the panel manually using this MCB. Now that we have electric power inside, we should distribute it between different devices. First, we need to supply the utilities of the control panel, like the lamp, fan or heater, and socket. Let's consider a separate MCB for each of these devices. The standard way to connect the wires to an MCB is to connect the input wires to the top side and the output wires to the downside connectors. So, I take the power from the main MCB and connect it to the input of the other MCBs. This one is for the socket and the lamp. This one is for the fan. And this is for the control's power supply. To step the power down from single-phase 120 volts to the control voltage, which is 24 volts for example, we need a 24 volts power supply with an appropriate amperage capacity. The next step is to connect the 120 volts to the power supply. Take the 24 volts from its output and distribute it over some terminal blocks. As you may know from our previous videos, by using a terminal block, you can join two wires to each other. To connect all of the terminal blocks of the same purpose, we can use a terminal strip jumper. I should put it in the middle holes of the terminal blocks and fasten its screws. In this way, all of these terminal blocks will have the same voltage of 24 volts. I have planned to dedicate this power supply to the PLC CPU and its input-output modules to even protect them more against any faults that may happen outside of the control panel. Therefore, I should consider a separate power supply with sufficient amperage for feeding the devices at site, such as instrumentation devices. I repeat the same procedure for this power supply, but this time, instead of ordinary terminal blocks, I consider some fused terminal blocks to protect the power supply against drawing extra amps by the devices at site. I'll explain that with a practical example in a video about troubleshooting the control panels. Alright, it's time to add the PLC and its input and output cards. Think of the PLC, or Programmable Logic Controller, as the brain of the whole control or automation system. I connect the 24 volts to turn it on. I would connect separate 24 volts from these terminal blocks to each digital input and digital output card to turn them on. Normally, we do not wire the PLC card channels directly to the devices at site, either digital input or digital output cards. It means that if our digital input card has 16 channels, then we should install 16 terminal blocks corresponding to that. It is the same story for the digital output card. You might be wondering when we have more DI or DO cards, we'll be in lack of space for all of the terminal blocks. It is true, of course. If we have a huge number of inputs and outputs in the process, the layout of the panel gets completely different from what you see here. There should be another panel, known as the marshalling panel. In this way, we'll transfer all of these terminal blocks to the marshalling cabinet. In some enclosures, the rear section of the mounting frame can be used as the marshalling part of the panel, so that we can merge the control and marshalling panels and save lots of space in the electrical or control room. Now, let's have a brief overview of how to connect the sensor to our control panel. Take this photoelectric sensor as an example that is installed adjacent to the conveyor and is supposed to recognize the boxes that are passing by on the conveyor. As this sensor requires power to operate, I'd connect the 24 volts to that from the second power supply's terminal box. It should return these 24 volts to the PLC input card in case it senses a box or object in front of that. So I'm gonna go ahead and connect a wire from the sensor to its corresponding PLC's input channel. After this sensor informs the PLC about the presence of the box, the PLC should command the next conveyor's three-phase motor to start turning. To do so, we should add a contactor to our control panel. Connect a three-phase power to its input and lay a cable between the contactor and the motor connection box. Actually, when we have three-phase power within our electrical control panel, the arrangement of the panel would be somehow different from what you see here. But let's take it easy and move on for now. As soon as the PLC output card energizes the contactor, it will transfer the three-phase power to the electric motor. You'll also find some relays in the control panel to command the single-phase actuators and control devices at site like solenoid valves. As you'll see in future videos, the electrical panels and devices are scattered throughout the whole plant, and they should be interconnected to each other despite the different communication protocols they might use. So the other category of devices you'll definitely find within any electrical control panel are industrial communication devices, such as Ethernet switches, or some gateway devices such as Profibus PA to Profibus DP couplers. Let's cover the docks and you'll see how the panel looks neat and tidy. I really hope you've enjoyed this video. I deliberately left some of the details for future videos to first touch the basics and dive into the details step by step. I'll explain the details of each component of the electrical control panel and the panel enclosures, different types of electrical panels in a project, and generally the electrical layout and architecture of a typical factory in future videos. So stay tuned!